I'm going to talk today about estimates of SNP heritability using HE regression, Haseman Elston regression, and GRIML, genomic RIML, right? Restricted maximum likelihood. And then talk a bit about biases. I think I talked, yesterday just a bit about what, in response to the question, what keeps me up at night, what I worry about. I'm one of these, I've always, in my career, been worried about biases and methods of estimation. And we've done several recent projects on these biases in GRIML. If you want to blame somebody for this talk being long and complicated, you can blame Jonathan Beauchamp, because last night at dinner we were talking about, and I said what I was doing, and he said, "Oh, are you talking about that tomorrow?" I said, "No." I felt like it was a bridge too far. He's like, "Oh no, you really should talk about that." So I went back to my hotel room last night and added the part that we had talked about. And I was like, well, if I'm talking about that, I should include this too, because it just makes perfect sense to include that. So then I included two new parts of the talk. Then I realized, well, I can't include all these things and still include all the stuff I was trying to include in the front. So I took all that out, and by the end of the night, it was a totally different talk than what I had originally intended to do.
My suggestion was just to use 3 slides on this.
I'm still going to blame you, Jonathan, because if it weren't for you, this never would have happened. So, and the talk is going to be way too long. I know that going into it, probably too long, and I probably won't finish. But I do include it all in there for you to take a look at, and I'll try to keep time and determine what it is I'm going to skip or not as we go forward. Okay, so the outline is first I'll talk about estimating SNP heritability using regression. This is really Haseman Elston regression, or GRIML. So it's just kind of a basic kind of intuition behind how these things work. Then talk about bias, different ways that these things can be biased, and at least for the first two, how we can overcome those biases. The third one has proven more intractable, and I'm not really sure if there's a way to do that. At least we haven't figured out a way yet to correct for that bias. There is also going to be a bias here, which is going to be due to natural selection, which is going to work opposite of this. But that's something that we haven't yet tackled, and maybe somebody like James Lee can do that. And then I'll talk a bit about best practices. I don't know if I'll get through all this, but we'll see. Okay, so first of all, just kind of the intuition behind how these estimates work. So this is probably a bit of a review for what you guys have been hearing, but the sum of the R-squareds from significantly associated, genome-wide significantly associated SNPs is typically much, much less than the heritability of those traits. We call this the missing heritability. And the question is, well, what is making up what's making up that missing heritability? Why are we getting sums of those genome-wide significant hits that are like less than 5%? And we think that the heritabilities, although we could always be wrong because it's due to bias in the family methods, but we think those heritabilities are typically about 0.5 plus or minus 0.2. Possibility that seems increasingly likely is what Fisher called the infinitesimal model. When he introduced that, it's not really clear if he meant it as just kind of a mathematical convenience or if he really meant it to be taken literally, but it's increasingly seeming like that's closer to the truth than not. So the infinitesimal model is just that there's a ton of causal variants out there, and each one of these has a very, very small effect on the trait. So therefore, what's causing this missing heritability is just a whole lot of type 2 errors. We are failing to detect things that are actually truly associated with the trait. So we can use genetic similarity at SNPs to test this hypothesis. So this is the original motivation behind GCTA. Who's familiar with, I'm just curious, who is familiar with GCTA? And, oh wow, okay, so a substantial number of people. And then who's used it? Who's used GCTA? Okay, that's just helpful for me now. Okay. So the way this method works is that you determine the similarity between all individuals at their SNPs, and you relate that to the similarity of all individuals at their phenotypes. Okay, so you're really kind of regressing phenotypic similarity onto genetic similarity. And there's multiple ways that this can be done. There's Haseman Elston regression, just regular regression approach, which I'll start off with. There's mixed effects models like GRIML, which is instantiated into GCTA among other packages. There's Bayesian approaches like Bayes-R, and there's LD score regression. I'm only going to be talking about these first two in this talk. Okay, so let's talk about Haseman Elston regression first. So we can call theta ij. Ij is going to index individuals. So here we have two different individuals, and all that is just the product of their two centered phenotypic scores. Okay, so you take their phenotype and you subtract the mean from that phenotype from every individual. In this case, we can do one better and we can actually standardize those. So these are actually z-scores in this case. If they're not z-scores, then everything I'm talking about are going to be covariances. If they're z-scores, everything I'm talking about are in correlation terms. Okay, so these are the product of two correlations. Okay, so the expectation of theta ij is just the covariance between those people. It sounds weird to think about a covariance or a correlation. In actual terms, this is a correlation here because these are, if we consider these to be z-scores, this is a correlation. It sounds weird to talk about a correlation between two people, but if you know the means of both of the variables, here those are 0, and if you know the standard deviations of both of those, in this case they're 1, then a single product between two people, right, a single observation of the product between those is an estimate of the correlation. It's not a very good estimate, but it is an estimate of the correlation. And here it's going to be more obvious because we're going to have a lot of people, we're going to have a lot of ties. And so if you take the expectation of a bunch of people who have the same pi hat, the same genetic relatedness, the mean of all those is going to be the correlation between those. I'll show that in the next slide. I think it'll be more obvious. So the expectation, what we're going to do is we're going to model this as a function of the genetic relatedness. We're going to allow that observed correlation between two individuals to vary as a function of how genetically related they are. All right, so we're just going to model this in a simple ordinary least squares regression. So the expectation of that product, of the product of two phenotypes centered, given their pi hat is equal to beta naught plus beta hat 1 times their genetic relatedness, which we're denoting as pi hat ij. That's the genetic relatedness between two individuals, and we'll talk about how we calculate that genetic relatedness in a second. If you do this, then that slope of that regression is equal to the heritability. The slope of the regression that is equal to is an estimate of the heritability. So let's go through what I mean by all these terms. So let's go back and think about the twin model in this way of thinking about Haseman Elston regression. The pi hat, the genetic relatedness between MZ twins is 1, right? They're identical at all loci. And the additive genetic correlation, the pi hat between DZ twins is 0.5. They share, on average, half of their genes. Now, if we'd measured pi hat here, this would be exactly 1, as it is. And the 0.5, there'd be a bit of variation around this. The standard deviation among siblings at pi hat is about 0.04. So this is demonstrating a situation where we're just guessing at what their average pi hat is, which is 0.5, rather than actually measuring the pi hat, in which case there'd be a little bit of spread around these. Okay? So these are all the products of MZ twins. And if you think about it, you just take the average of all those products, and that will be equal to the covariance, or in this case, the correlation between MZ twins, right? Think about what the formula is for a covariance. It's the expectation of xy, right? Or in this case, expectation of zi, zj, minus expectation of x times expectation of y, right? Well, we know that the latter two terms are 0. Expectation x is 0. We centered. Expectation of y is 0. So the expectation of xy, or expectation of zi, zj, is equal to that covariance. So the average of all those scores is the MZ covariance. That's going to be denoted by that point right there that the regression line goes through. The average of the DZ products is the DZ covariance. And so what is the difference between those? The difference between those two scores is half the slope. So we've got to multiply this by 2. The difference between the MZ correlation minus the DZ correlation, 2 times that is equal to the entire difference between not being genetically related at all and being exactly genetically correlated. So the slope of this line can be thought of as, right, just the slope. It is literally the slope of those points. It's going to go through the mean of these set of points and the mean of those set of points, which are the covariances. That's also equal to twice the difference between MZ correlation minus DZ correlation. If you think back to how we figure out what an estimate is of VA or heritability if you're using correlations of, in a classical twin design, you think, well, it's the correlation of MZ minus correlation of DZ, that whole quantity times 2, right? Twice the difference between those. And that's also the same thing that this slope is showing. So this is just kind of an intuitive way of showing that that slope is equal to the estimate of the heritability. What we can do instead, and what we do typically in GREML, is we use unrelated people to get at the same estimate. So here we've been using related people. Now we could think about getting those products, the same set of products between all individuals in a sample that aren't necessarily related. Now those are going to typically be very close to 0. So the mean of those, by definition, because we're using the sample itself to define what the mean of the genotypes are, the mean of that will be exactly right around 0. The mean pi hat will be 0. So there's going to be some negative values and some positive values. It might sound weird to have a negative relatedness, but that just means you're less related than the average pair of individuals in the sample. Okay? So there's going to be some variance around this. That the standard deviation of pi hat will depend on the number of markers, but for a genome-wide array, it's typically about 0.005. Okay? So one thing you know about regression is that the power of your regression depends a lot on the variance of your predictor. So here, we've got a lot of power because we've got a lot of differences in pi hat. But with GREML, what we do is we remove the related individuals and we only use the unrelated individuals. Now the slope is not going to be identical to the slope we got before for reasons that will become apparent as we talk, but you're still getting an estimate of the heritability. This is called an estimate of the SNP heritability. That's why I've changed this down here. And we're using unrelated individuals to get that estimate. So what this is saying is that to the degree to which individuals are phenotypically similar, given, well, let me say that again. What this is measuring is the degree to which people are phenotypically similar predicted from their genetic similarity, given their genetic similarity. So the degree that people are more phenotypically the same when they're genetically similar is going to be evidence for SNP heritability. If there's no relationship between how phenotypically similar they are and how genetically similar they are, we get no evidence for SNP heritability. Okay. So the question is, why do we remove? One question might be, why remove related? I'm going to go through GREML right after this, but I'll pause for just a second. So, what's the motivation behind removing related individuals in these analyses? Anybody have thoughts on that? Yep.
Their relatedness is also confounded with their shared environment.
Okay, so there's several reasons, but this is a big one. One is that we know, and we've known for 30 years, that there are problems with using close relatives to estimate heritability. And one of those, for example, is that shared environmental factors are, in the presence of non-additive genetic effects, can lead to biased estimates of your additive genetic variance. And just in general, we'll get biases using close relatives, getting estimates of heritability unless various assumptions, which are probably often not met, are strictly met. And so we know that those estimates are going to be somewhat biased. So that's one motivation. Any other ideas of why we might use unrelated individuals rather than family members to get estimates of heritability? James?
Well, this is implicit, I think, in your last answer, but contributions of non-additive genetic variants are going to be much reduced.
That's exactly right. Yeah, almost 0. So we're really not, there's really no confounding here of non-additive genetic effects either, whereas in the twin method, part of the reasons that MZ twins are more correlated than DZ twins is due to non-additive genetic effects. MZ twins share all the non-additive genetic effects, DZ twins only about a quarter if you're talking about dominance or additive by additive epistasis, and an eighth if you're talking about additive by dominance epistasis, and so forth as the degrees of epistasis increase. So that's another motivation. We're getting more of a kind of a potentially pure measure of heritability. Although there's a lot of, we're going to talk a lot about how we interpret SNP heritability. But any other thoughts on why we might do this? Okay, so I think another motivation is that it gives us insight into what's called the allelic spectra of causal variance. And this is going to become clear as we move forward. But what this is actually a measure of is the degree to which the degree to which causal variants are tagged by the variants that we used on the array to estimate that genetic relatedness. Okay? So that SNP heritability is going to reflect the degree to which the causal variants that are actually out there are tagged by those causal the SNPs that we use in the array. So if we know the SNP, if we know the true heritability is 0.5, and we're using common markers and we're getting a SNP heritability of 0.45, that tells us that most of the causal variants are being tagged by whatever we use to make that genetic relatedness matrix, or to build that pi hat, those pi hats. And if those are all common, if those are array-based SNPs, that's telling us something about the causal variants. It's telling us in that case that most of the causal variants are very common, which is an important thing to know. If, on the other hand, it's the reverse and we get a SNP heritability of 0.05 using an array GRM, and the true heritability we think is 0.5, that's a huge discrepancy that would need to be explained. One possibility that would be consistent with that would be that a lot of the causal variants are very rare. There's other possibilities too, like that the original estimates were biased upwards. Okay? And as we use more and more, increasingly we're going to be using imputed data to build those GRMs, to build these pi hats. All right? As we do that, we're able to directly estimate the allelic spectra of the underlying causal variants. So that's another exciting thing. And there's a lot of other motivations behind doing this as well. It allows us insight into biological annotations, so we can get some insight into whether it's genic variants that seem to be more important, or if it's variants under selection, variants under different levels of LD. These can be done with GRML. It's probably a little bit easier to do these in LD score regression, which we're not going to cover, but that is going to be talked about.
It was already talked about.
Oh, it was already talked about. Okay, so is a lot of this review for people, or?
No, this is great.
Okay. All right, so let's talk about GRML, and we're going to spend a lot of time thinking about the interpretation of this estimate, given what it was that went into making that GRM. And by the way, feel free, obviously, to interrupt as we go forward if there's questions or clarifying comments or something that needs to be clarified. Okay, so let's just take a very simple toy example to demonstrate GRML as opposed to HE regression. So here we have 3 individuals. We have 2 covariates of fixed effects, and then we have 3 SNPs. All right. So at each of the SNPs, I guess here we'll start here. Y is a vector of the observed phenotypes, the outcome variables, so whatever it is that we're interested in measuring the heritability of. X is just the design matrix, and beta hats are the fixed effects that correspond to that design matrix. So these are covariates. In this case, Q is 2 because we really only have a single covariate and then an intercept term. Z is going to be the matrix, the N by M design matrix of SNP scores. Right? There's N individuals and there's M scores. Usually this is tens of thousands and this is potentially millions. Right? It'd be hard to put that on a slide. So, and in fact, what this is in this case is it's the Z scores for each of those SNPs. So we take each SNP score for each individual. That's why all these numbers are the same, because I actually should have done this differently. But in this case, this person's a genotype 2, and this is 0, 0, 0, 2, 0. I think that's probably why these are all the same. I should redo this and use better numbers there. But in this case, right, this is a single column of a particular SNP across the sample. So you can get the mean of that SNP. You take that each person's score minus the mean, 2 times the p, and you divide it by the standard deviation. So these are all z-scores at each person's SNP. Okay. And we multiply this by SNP effects. This is the model. We're not actually going to estimate each of these SNP effects, but we're going to estimate a single parameter. We're going to assume that they're normally distributed and estimate their variance. And these are the residuals. All right. So we usually, as I just said, we're usually not interested in estimating each of these UIs because M is usually a lot greater than N, right? And because such individual estimates would be unreliable, as we know from LD score regression when we try to estimate each one individually. We can't do it simultaneously for this reason, right? It's, M is, the number of predictors is a lot bigger than the number of data points that we have. So what we have to do in LD score regression is estimate each one individually. Doing that, though, leads to a tremendous amount of error in that PGS that we create. And we know that that will therefore lead to a downward bias in the estimate of SNP heritability that only goes away as the sample size approaches infinity. This is something that Patrick talked about yesterday. Here we're doing something different that should give us an unbiased estimate of the SNP heritability. All right, so we're not estimating each of these individual effects like we would be in a PGS. Instead, we're going to just assume that these are normally distributed and estimate their variance. We're going to estimate a single parameter. Yep.
So I'm a little worried about this. It looks like you're regressing out the things like age and sex from Y, but not from.
Yeah, this is actually not quite exactly right. It's done simultaneously in a maximum likelihood way. I should probably just leave this out because I think it just leads to confusion. But I mean, I think I'm just trying to kind of give an intuition behind what's happening. In reality, these are all being done simultaneously, so it should be controlled for here as well. Okay. So we assume that those U's are normally distributed with mean 0 and variance equal to sigma squared U. So these are the genetic effects at each individual SNP. So we're assuming that all SNPs have an effect. Okay? And the variance of those effects is distributed normally with mean 0 variance sigma squared U. And therefore the entire genetic variance, additive genetic variance, is going to be equal to the sum of all those sigma squared U's. Right? This assumes independence of effects and no LD, which is another assumption that these things are not, these are independent. You can see this because you're summing across all these terms. We're just taking that M times the number of terms that we're summing across times the variance of U to be the total additive genetic variance. So there's another assumption of G Rimmel, but we'll talk a lot about that too as we go through, that there's LD between those. There's LE, linkage equilibrium, between those SNPs. But therefore, if this is true, then the total additive genetic variance is just going to be equal to M, the number of markers, times the sigma squared U, their effects. So we can think about this now as the variance, covariance of Y, which is just the outer product of that Y vector, is going to be equal to ZZ prime times the variance of U times the identity matrix times the variance of the residuals. So the outer product of Y, right, is just, we had here, let me go back just a sec. Right, we had, sorry, this is a little bit funky. Okay, let me just, sorry. Okay. We have here an n by 1, so if we take an n by 1 times a 1 by n, we'll get an n by n matrix, right? That's the outer product of Y. Each one of those is going to be a product term between two individuals like we talked about before. Each one of those will therefore be a single estimate of the covariance between those people, given that we know what the means and the variances of Y are, okay? So that's what this is. This is an observed n by n variance covariance matrix that comes from the outer product of Y. This is the n by m, right, times m by n matrix, right, which is going to be an n by n matrix. And what are each of these terms? On the diagonal are estimates of of the genetic relatedness of people with themselves. Okay. On the off diagonal are the estimates of genetic relatedness between individuals. Now, as this becomes very large, right, this is what these turned out to be in this toy example. As this becomes large and m becomes large, this diagonal would become very close to 1, and the off diagonal would become very close to 0, because we're using unrelated individuals in this. The mean of this off diagonal, by definition, should be very close to 0. And its standard deviation is going to depend on m. Its variance is going to be 1 over m. So the standard deviation will be the root of 1 over m, where m is the effective number of SNPs, the number of effectively independent SNPs. And that turns out to be in a genome-wide data set to be about 0.005. All right. So that what is each of these actually? If you do the matrix multiplication, this well, actually, let me go through this first. So So ZZ prime is, I said it was this, it's not actually quite that because this is ZZ prime over M. So how does that work? So you take ZZ, this is the outer product times ZZ prime variance U. Well, we know that variance of U is actually just the variance of A divided by M by virtue of the variance of A is equal to sigma squared U times M, right? So if we take that M outside of here, what we'll do is we'll take ZZ prime, right, which is the sum of cross products matrix, and divide it by M, which is going to give us a variance covariance matrix, or because these are Z scores of genetic scores, a correlation matrix of genetic values. So we take ZZ prime over M and we call that G. This is what's called the genetic relatedness, genetic or genomic relationship matrix at each SNP. Each of those elements, we're dividing by M because we've moved that out here, is equal to the sum of X minus 2P for person I, individual IJ. I'm sorry, no, this is across SNPs. So this is for SNP I, person J, and SNP I for person K, right? We remove the means of those SNPs and we divide by the variance, all right? So this is an estimate at each SNP of the correlation between those people at that SNP, okay? We then sum all those correlations across all the SNPs for each individual and we divide by M. So the way to interpret these off diagonals is the average correlation across all the SNPs of people's genetic scores. How correlated are people on average at all the SNPs between two people, for all pairs of people in the sample? As that number goes up, what that's telling you is people are more similar to each other. A pair of individuals is more similar to each other across all the SNPs that they have than expected on average, based on the average or typical similarity in the sample. And as that number becomes negative, it means that that pair of individuals is less genetically similar than would be expected based on the average similarity in that sample. Okay? So pi hat is really a measure of the average correlation across all SNPs between a pair of individuals. Okay? Yep.
Should we expect the diagonal to be close to 1 or actually 1 by definition? Or
No, because you can be more similar to yourself than expected on average. Okay, so if this is a measure of inbreeding, right? So if your parents are more similar to each other, right, than expected on average, in other words, if they're, say, cousins, then your similarity to yourself is going to be higher than it would be than other people's similarities to their selves. Your own genetic relatedness is higher than would be expected. So you will see some cases in a sample, especially a highly inbred sample, where these are estimates of F. So that diagonal minus 1 is an estimate of the inbreeding coefficient. And you'll see sometimes that those get upwards of like 1.05 or 1.1, which would be indicative of potentially cousin-cousin mating. Yeah?
I think I missed the part where you explained how one can be correlated to oneself, and it's probably because I'm still kind of in an old school variable setting where, where I'm thinking of an individual having one value for each variable, and then of course you can't correlate that.
Right.
That's a perfect correlation.
Yep.
So how should I think about it?
I think the way to think about it is that if you're homozygous at a lot of variables, right? That's saying that that the SNPs that you got from your mom and the SNPs that you got from your dad were more likely to be similar than it would be at random. If it were random, you'd be homozygous about p squared plus q squared % of the time. If you're inbred, if your parents were actually similar, you're going to be homozygous more often than would be expected. And so the degree, so one way to think about what this is a measure of, this diagonal, is the degree to which you're homozygous more expected than would be the case under Hardy-Weinberg equilibrium. Yep.
Would associative mating also have an impact on that? Or is it very minor?
It's extremely minor. Yeah, because assortative mating leads to similarity at all the causal variants, right? And so assortative mating does lead, if it's just, if it's a single variant, it's going to have the same effect that inbreeding would have, which is pretty large. But for a polygenic trait, the degree of which assortative mating increases homozygosity is minuscule. Basically 0. Okay. So Rimmel intuitively finds values of these two parameters, sigma squared A and sigma squared E, that maximize the likelihood of the observed data over here. Intuitively, the way that you can think about it is it's mucking around, it's changing these values of sigma squared A and changing these values of sigma squared E in order to make this implied variance-covariance matrix as similar to the observed variance-covariance matrix as possible. So, I mean, you could, yep, James.
So, you don't want to get into a deep dive here, you can just move on, but
Uh-huh.
What always confused me about this, so we have y prime, and it seems to me that var means that we're just taking the expectation of that over random samples of the same size. And so that will turn, E prime into, identity matrix times the residual variance. But how could this expectation that you're taking over random samples of people convert the vector u prime, the matrix u prime into relatedness times, because it seems to me that the people and the SNPs are totally different objects. And how can you
So is this I think yeah, this is interesting. You've actually written about this before in the Lee and who was your co-author on that paper? Chow, that's it, the Lee and Chow paper. Yes, this is an issue about what it is that's actually random in the model. So G. Rimmel is assuming that it's like thinking that the causal variants are being resampled each time that you do this. So the causal variants are random, and what's fixed are the people. But in truth, in reality, it's the opposite of that probably, right? It's that the causal variants are the same, and what's happening each time is you're resampling people. So people should be the random component to this. I think it doesn't actually make sense. Okay, I think it's actually wrong, but I think in practice it doesn't actually matter. Yeah, but I think it's an interesting point. I mean, I never had thought about this until I read your paper actually, and then it got me thinking. Well, that's probably, you're right, I think. And then I ran this by Peter and Mike, and they were like, yeah, that's right, but who cares? So yeah. So yeah, it's an interesting point.
Has the same kind of issue, where the standard errors that they calculate are based on the idea of randomizing across SNPs and not randomizing across individuals.
Okay.
But this sounds like it's implicitly a Bayesian procedure where your sample is fixed and you don't know the truth about the world, so you have uncertainty that you think of as randomness, and then you're effectively taking some kind of uninformative prior, so it converges to a maximum likelihood procedure.
Yep. Yeah, interesting. I should have been a lot more nervous giving this talk, having this audience here. So, yeah, I'm glad I didn't think about that before I gave it. Okay, so let's think about how to interpret SNP heritability from these models. So if close relatives are included in your estimates, like in that first slide I had where we included MZ and DZ twins, or even if you're including just siblings, then you should interpret these estimates of SNP heritability as you would from any family-based method based on the individuals that make up those relatives. So if you're using siblings, the estimate that you get of SNP heritability is the same estimate that you'd be getting if you did just a sibling-based heritability analysis. In other words, you're just doubling up the correlation between SIBs to get the estimate. Why? Because siblings, and certainly DZ twins and MZ twins even more so, have an enormous influence on the regression, and G. Rimmel have an enormous influence because they're like 100 standard deviations above the mean. That's probably almost exactly right for DZ twins. They're about so if you think about doing a regression in which you have most of your scores really close to 0, and then you have a handful that are 100 standard deviations above, well, guess what? Those are the ones going to have all the influence on that regression plane. And so I've seen this a few times where people throw in relatives because it reduces the standard error, and then they continue to interpret the estimates of SNP heritability as you normally would. That's not right. I mean, the estimate of SNP heritability really is just, you just did a family-based estimate of heritability there. So it's something to keep in mind. If you're removing related people, so say you use a typical cutoff of 0.05 or a cutoff of 0.025, and yep.
So I have a question about that. If you did a twin study, you get this confounding of the non-additive genetic variant.
That's right.
But here, if you include twins or close relatives, you're still just taking a covariance, which is a linear operator to measure the relatedness across individuals.
Yep, there's still going to be a confounding between that additive genetic
I see.
matrix and the non-additive genetic matrix, because MZs, if you're using MZs, are related at 1 for the additive genetic, they're also related 1 for the non-additive genetic. So even though you don't model the non-additive genetic, it's still going to potentially influence that regression slope. Yep. And the main motivation, the reason that we remove related individuals here, is because we want to try to remove that confounding. Oh, this thing's kind of dying away. We want to remove that confounding between shared environmental effects and genetic similarity. So one of the important assumptions that we use here to get an estimate of SNP heritability when we do this is that genetic similarity is not going to be correlated with environmental similarity. All right? If that's violated, we will get biased estimates of SNP heritability. And there's been a lot of discussion about how often that actually will occur. Yeah?
What will happen if you sort of, go beyond first cousins? So, your dominant component will sort of decay much faster than your additive component.
Yep.
And I'm guessing your sort of shared environment will also decay pretty quickly if it's sort of.
Well, that's the crucial assumption here, right? So the question is, well, what if we don't use siblings, because they're sharing a quarter of the dominance variance, but instead we use, say, second cousins, which really shouldn't share any, they don't share any dominance variance. Does anybody even know what the additive by additive epistatic relationship is between cousins? I said second cousins. I don't remember. It's either 0 or really close to 0, so it's going to be very poorly confounded with that too. But I think the concern here and the reason that people don't do that and they use a more stringent cutoff like 0.05 than say 0.125 is that, first of all, there's not going to be many usually cousins in a sample like this, the way that these are usually collected. But the other motivation is that there's a concern that with cousins certainly, you could still be, those are going to be huge outliers on the regression plane still, right? They're going to be like 25 standard deviations above the mean. So they're going to have a big importance, even if there's not a lot of them. And there's a concern that they're going to be more environmentally similar than would be expected based on just random pairs of individuals. And to the degree that's the case, and to the degree that environmental similarity leads to phenotypic similarity, you're going to get an upward bias in your heritability. Yeah. Are there other questions along these lines? These are good questions. Okay, so and there's no way I'm going to get through this talk, so that's fine. I kind of anticipated that. But I think it's more important to go slow and think through these things than to get to all the fancy stuff at the end. So if we use unrelated people who are less related than, say, 0.05, which is kind of an arbitrary cutoff, then it should be the case that the estimate of additive genetic variance that we get from this, or SNP heritability, perhaps I should have said, is uncontaminated by shared environmental effects and non-additive genetic effects. It doesn't therefore rely on these assumptions that you have to make in family studies. So for example, the kind of the core assumption that we make in twin studies is that the genetic correlation of MZs is greater to the genetic correlation of DZs for genetic reasons only, and that there's no kind of what's called special MZ twin environmental effect. And if that's violated, then these twin assumptions are completely off, completely wrong to the degree that that's violated. So we don't have to make those types of assumptions about those, at least the strength of those assumptions is much reduced, because all we have to do now is assume that very small differences in genetic relatedness among ostensibly unrelated people don't correlate in some way with environmental similarity. There's a very easy way that that can happen, by the way. Can anybody think of what that would be in these types of studies, where genetic similarity would be correlated with environmental similarity?
Where your genetics is helping you choose the environment or something like that?
Well, it's not where I was going. I mean, I think that in that case you can make, it depends how it's working, but you can make a case that that's just a kind of an extended phenotype of the gene, if it's kind of active, or what they call provocative, is that right? No, active gene environment correlation. Am I using the right? Evocative, that's it. I was saying provocative. It's like, no, that's not it. Evocative gene, yep.
I don't know if this is far afield from what you're going for, but to the extent that groups are still in their indigenous regions where they have been for thousands of years, there should be sort of just geographical environment
Yeah, this is basically where I was going. So, no, this is basically right. So I think a real concern in these studies has been the degree which stratification might bias these estimates upwards. And so stratification is where you've got a sample that includes mixed people of mixed ancestry. And obviously people who are more similar ancestrally are going to be more similar genetically. And if that also correlates in some way with phenotypic similarity due to whatever reason, cultural reasons potentially, then you will get a biased estimate of that SNP heritability. So it's typical that people do these studies on an ancestrally homogeneous sample. And even at that, people will typically control for 5 or 10 principal components to ensure that we've removed any effects of just those basic ancestrally, any of this phenotypic similarity that's correlated with that basic ancestry. Okay, so the degree that, so we get evidence of SNP heritability to the degree that similarity at SNPs corresponds to phenotypic similarity. So therefore, SNP heritability is a proportion of phenotypic variance that's due to causal variants that are tagged by, or in other words, that are in LD with the SNPs that were used to make that genomic relationship matrix, right? And that's the crucial point which we're going to hit on a lot as I move forward here. Yeah.
I have a question about the sort of like using the genomic relationship matrix.
Uh-huh.
To what extent, like if, say that I have like, I mean, I don't know how many plugin scores I have derived right now, but
Yeah.
there's like 100 or 50 or whatever there is for all these obscure traits. So if I have like 2 columns of data and one is like person A and person B, and it's just like all of their different scores, meaning, yeah, I guess, to what extent does their like relatedness correspond to like the similarities and like their specific scores? Does that make sense?
No, I kind of it was probably my fault.
No.
But
So like, I guess just the correlation between 2 people on any given score,
Uh-huh.
like how closely does that match the correlation between their just overall genomic relatedness? Is it?
that is kind of what this is we're trying to get at here. We're estimating how, so for a particular phenotype, you know, how similar is what is the relationship between their phenotypic similarity to their genetic similarity? That is the essence of where we're getting these estimates of SNP heritability. And if that does predict, if genetic similarity does predict phenotypic similarity, then that's evidence of SNP heritability.
Just to remember that the polygenic score is a measure, a noisy measure of the additive genetic component for a phenotype.
Yeah.
And the variance explained by the additive genetic component is the narrow heritability. And that's essentially what we're estimating here, except we're estimating it for just restricted to the set of SNPs that are measured.
Gotcha. Yeah.
But it sounds like you're saying you want to measure relatedness by how similar their polygenic scores are for a bunch of different traits. Is that?
That's sort of the opposite. Yeah. But,
Yeah. So I mean, I think that it's going to be related, except you're going to be weighting SNPs that have higher values, like higher weights that you put on in each of the different scores. So I mean,
yeah, it seems like there'd be no reason not to do that. I guess.
I don't know.
If you do it for a particular polygenic score, then I think you're getting at something similar, although there's noise in the polygenic score, so that's
Yeah.
the idea of this random effects approach is to get rid of that noise that would lead to attenuation. If you do it for many polygenic scores, then you're effectively doing some kind of averaged SNP heritability over all of those traits that you're including.
Yeah. The slides that I took out of this, right, thanks to Jonathan, were were all about polygenic risk scores, or PGSs, and then why those are downward biased estimates of the SNP heritability. Essentially, it's just you're summing across a lot of noise, and the noise of those typically swamps the true signal, and therefore, you know, it's one of these issues of error in the predictor. You're going to get a downward estimate, a downward bias estimate. So unless your sample size goes to infinity, and that.
But I think he's just talking about populating the GRM.
Okay.
So he would just use the scores to fill out the GRM, and then you would still estimate the sigma squared.
Okay, so you use the PGSs to fill out
So you're saying
the
so
product of
correlation
PGSs.
SNPs, you look at correlation of the polygenic scores.
Huh.
And so I mean, I think that's an expectation should probably give you the same thing.
But those PGSs, the scores are based on some phenotype, right?
Yeah, but ultimately they're just weighted sums of SNPs.
Yeah.
And so
Yeah.
so if you did a correlation of the polygenic scores, I think what you're just going to get is you're going to get
Wow,
relatedness
yeah.
weighting SNPs that are happening.
I think you're going to get a
at the same
really
time.
mucked up estimate, right? Because you're going to be overweighting SNPs that show the most evidence for association, right? And I think that's going to give you a GRM that's going to give you a really upward biased estimate of heritability. I don't know. It'd be something to look at. I mean, it wouldn't be hard to do. I mean, weight the SNPs by their association and see what happens. My guess is you get a big upward bias. Interesting, yeah. Okay, so why care about this quantity? I talked about this a second ago. So for one, it gives us an estimate of the aggregate importance of the CVs tagged by SNPs. And increasingly people are using imputed SNPs here, which I'll talk about in a second, and gives us an upper bound of the total sum of R squared that GWAS could in principle detect as our sample sizes become very large. As imputation improves or we obtain large sample sequence data sets, SNP heritability becomes an estimate of the full heritability, in other words, due to both rare and common causal variants. So although SNP heritability is its own set of biases, which we're going to talk about a lot, those aren't the same as those that affect the twin family estimates, and therefore such triangulation, if we get some estimates of SNP heritability and some estimates of family heritability, and they all kind of seem to be making a similar picture, it becomes very difficult to kind of argue these away, as some social scientists want to do, that these traits aren't really heritable because the special MZ twin environment assumption was violated. Well, that doesn't hold for these types of estimates. So if we're getting an estimate here that's about, say, half the estimate that we get for family-based estimates, which is kind of on line with what we might think for a trait that's affected about half for common causal variants, it becomes difficult to kind of explain it away, at least with that. So then people have to come up with new reasons why these might be biased. And I'm not saying these are unbiased. I'm just saying that it becomes increasingly tenuous argument to make that these traits really aren't heritable for various confounding reasons. And finally, we can use multiple GRMs in these GRML methods, and that allows estimations of parameters of interest like the allelic spectra of traits, how important different MAF bins are to trait heritability, and the relative importance of different biological annotations like whether DHS sites or DNA hypersensitivity sites or genes expressed in brain are important relative to those that aren't in those annotations. Okay, so I'm going to talk now about, this is kind of a crucial point, about the biases in SNP heritability due to the causal variant MAF versus the marker MAF. Typically this leads to downward biases in heritability, but there's nothing intrinsic about that. It can also lead to upward biases in SNP heritability, which I'll talk about. So this comes from a work that a postdoc of mine, Luke Evans, is doing now, and there's a paper that we're working on getting published. So I'm going to just kind of walk through the very basics of some of the stuff that we've done in that project. But this is really work that Luke has done, so I'll have a picture of him at the end. So what we've done is we took the haplotype reference consortium data set, which is a sample of 36,000 whole genome sequences. We had access to a subset of those, of 22,000 of those. And so what's important about that is that unlike data where you simulate the genotypes from first principles using like M prime or something like that, we actually have real sequence data with all the kind of interesting and complex genetic things that happen in real data. And from that real sequence data, we play God in a sense, and we simulate different causal variants of different MAF classes, of different, LD, if there's some kind of relationship between LD and the effect size. And then we see what happens across a lot of different methods. So we've done this. I'm just going to focus on some of the work that we've done with GRML, and in particular here with minor low frequencies of causal variants versus the GRM versus the SNPs. We took a sample of 8,500 of those from the UK with basically no stratification. The reason it drops this much is because we also wanted to, I guess for purposes here, we just wanted to get a very homogeneous sample to understand without any stratification issues, because stratification does play a role in these estimates, even if there's no confounding between the environment and stratification and ancestry. Even if there's no confounding there, it will still lead to biases in GRML, which, if I have time, I'll get to that. But for this, we took a very homogeneous sample, and we built GRMs either from, and what I'll talk about here is just from axiom array positions. The axiom array is the SNPs used in the UK Biobank, so we thought that was pretty relevant, given a lot of people are using that now. And we also looked at whole genome sequence variants. This is all the variants, in all the sequence variants that we had across the genome. And sometimes we restricted these to just all the common ones with the MAF of those variants over 0.01, and sometimes we used all of them all together. We did this as well for imputed SNPs, where we used an independent reference sample, sequence sample, to impute the SNPs and get from the axiom array. Those results turn out to be extremely similar to the ones just using whole genome sequence data. So we're going to I'll just report the whole genome sequence data to kind of keep it simple. But in practice, you're not going to have this. What you will have, though, is imputed SNPs. And so the point, I guess, is that the results from here are going to be very similar to what I'll be presenting with the whole genome sequence data. We simulated from a whole genome sequence, as I said a second ago. For each one of these, we drew 1,000 causal variants. We also did this with 10,000, and it made virtually no difference to our results, except for, interestingly, for LD score regression. So one of the kind of the crucial, it turns out, assumptions for LD score regressions is that you really do have this infinitesimal model. So you really do need a lot of causal variants for it to work out properly, which might be usually the case, I guess. So maybe it isn't so important. But at least here, we just simulated 1,000 CVs, which works just fine for GRML. We varied the MAF of the causal variants as well as the MAF of the SNPs. I should have said that there. So Y is just going to be equal to the breeding value of each individual plus some environmental noise that we added on, randomly distributed. And the GI, that breeding value, is just the sum of the SNP effects times the genetic score of each individual at each SNP, summed across the SNPs. Okay. This is just shows the distribution of the variance. Now, it looks weird, but that looks could be deceiving here because these bins are not the same size. If we did it, I kind of got this from Luke. I think I would have done it where we just had the same bin sizes. What you would see if these were all the same bin sizes, of each with a length of 0.01, a width of 0.01, would be something that looks basically exponential. But here, the bin size here for what we call, and the reason he did this is because this is how we define the variants that we're going to be talking about. These are very rare, which are MAF between 0.0003 to 0.003, which corresponds to a minor allele count of 5 to 52. The 5 is the minimum minor allele count that existed in the haplotype reference consortium, because they removed any ones that were less than that. What we call rare is between 0.003 to 0.01. This, I think, was called low frequency, yeah, 0.01 to 0.05, and these are common above 0.05. Okay, and that's the numbers of variants that you get there. This shows what is in the HRS, the haplotype reference consortium, and this is what's in the axiom array. So most of these, of course, are much more common than what exists in the HRS. There are some that are very rare in the axiom array, and these are just kind of variants in genes that people thought might be relevant, but those in practice have turned out to be kind of irrelevant. Yeah. So we simulated phenotypes from GRMs from common arrays. When we use when the causal variants are common, and the GRMs are just, here we're just talking about GRMs from the common SNPs. And the heritability that we're simulating here is always going to be 0.5. So the true heritability here is 0.5. So if you get something like this, we know our estimates are unbiased. So these are the 95% confidence intervals that overlaps the heritability of 0.5. So we have no evidence to believe that these estimates are biased in any way. All right. So when we use when the causal variants are common and they're built from a GRM of common SNPs, we get an unbiased estimate of the total heritability. We get an overestimate of the heritability when the causal variants are even more common than the SNPs are on the array. Okay? So here's a kind of a weird situation that probably doesn't exist a lot, but here the causal variants are like over 0.05. All of them are over 0.05, so none of the causal variants have anything less than 0.05, but the axiom array actually has several tens of thousands of variants. Maybe it's 100,000 variants or something under 0.05. And so on average, the MAF of the causal variants is higher than the MAF of the SNPs built that were used to build the array. And here we get an actual overestimate of the heritability. And the same token, here's probably the more usual situation. Here, the causal variants are rarer than the variants were the markers to build the GRM, and we get an underestimate of the heritability. This is typically what we probably are seeing in real data. But this just shows in principle there's no reason that we can't get an overestimate either due to MAF differences between the GRM and the causal variants. If we make the GRM not from the axiom SNPs, but from all of the whole genome sequence variants that are common over 0.01, I can't remember what it might be that these are over 0.05 and very common is over like 0.2. I should have asked Luke before I gave this talk. It doesn't really matter because the principle holds. But anyway, the point here is that just adding more SNPs doesn't do anything to this bias, right? We've created data, we've added a whole lot of SNPs into that GRM, but those SNPs are still all of that same basic MAF category, so it doesn't change this bias at all. So it's not an issue that we have fewer SNPs than we need. It's an issue that there's a discrepancy between the MAF of the causal variants and the MAF of the SNPs that we use to build the GRM. So the relationship between GRML-SC, SNP heritability, and MAF is that we get unbiased estimates when the markers have the same MAF as the causal variants. We get underestimates when the causal variants are rarer than the markers, and overestimates when the causal variants are more common than the markers. So therefore, MAF is inherently related to LD, which I'll talk about in just a sec, and LD is related to the biases and heritability that we're observing. So this is just a plot from Naomi Ray's paper in 2005 talking about LD. There's, you can do this type of thing yourself. It's not like she discovered this. This has been known for forever. But each of these plots, and by the way, I just realized before I gave this talk that this is messed up. These things should be together. So r squared over 0.5 is this line, r squared over 0.2 is that line, and there's r squared of over 0.8, that's that line, all right? And this is the maximum difference in allele frequencies that we could potentially get given that r squared, right? So if the r squared is 0.8, you're not going to be able to get much of a difference in the two allele frequencies, right? So for something to tag another variant, for a marker to tag a causal variant with a 0.8 r squared, that causal variant has to be really close in its MAF to the allele frequency to the whatever way I said. The marker has to be similar to the MAF, the AF of the causal variant, or vice versa. Okay, so if that causal variant has if the marker has reference allele is 0.3, that causal variant has to have a allele frequency very close to 0.3, no more than 0.05 difference. This is the same thing, but for the 0.5, and this is the same thing for 0.2. So the kind of the point of this is just that the minor allele frequencies of the causal variant have to be very similar to the minor allele frequencies of the markers for it to be well tagged. And if they differ very much, that marker is not going to be a very good tag of the causal variant. You're never going to get a SNP with a minor allele frequency of say 0.5 that tags a causal variant that has a minor allele frequency of 0.005. It's just not going to happen. Yeah.
So before you got here, last week I raised the question of at least statistics when you use d prime or r squared.
Yeah.
And I understand certain reasons for using r squared since it directly corresponds to shared variance explained. But I wonder in this context if d prime might offer some benefits since it's basically insensitive to differences in allele frequency.
Well, this is you want it to be sensitive to the difference in allele frequency because I mean what ultimately we're worried about is how well are we able to predict variants of different classes based on the markers that we have. And so r squared I think is the appropriate term. I mean d prime is just the covariance standard by the maximum possible covariance that you could get between those. And so so it's not really I mean d prime in these kind of contexts is probably not a very good way of estimating LD.
I only raise it because what you can have, you can add the d prime statistic of 1 and you got a rare variant of 0.02 and a common variant of 0.4 if all of the, every time you
The haplotypes of.
What?
Mhm.
So that's kind of why they use it for sometimes for haplotyping,
Mhm.
determining haplotype blocks. I don't know.
I think here it is R squared that we want to use because we're worried about how well we're able to predict the causal variance based on the SNPs.
I'm just struggling for, is there some way to reconcile the fact that, that with R squared definitely can't, that the differences in allele frequency are going to be a major limitation.
Mm-hmm.
And so that's going to place constraints on our ability to estimate rare variance in general. So I'm just wondering if there's an alternative to just sequencing more and more variants until we get.
No.
You know, there's a.
No. Well, I don't think that changing the metric that you use is going to change these properties that we're talking about. I mean, yep.
So I'm trying to sort of understand what you've presented in this slide and perhaps the previous slide.
Uh-huh.
So if you're saying that common sort of variants
Mhm.
are more likely to tag common causal variants, and if you're sort of applying a filter of a minor allele filter of greater than 0.05 and then running that in GREMA,
Mm-hmm.
does that mean, so I'm guessing we can think of additive heritability as additive heritability, contribution to additive heritability from common variants, contribution to additive heritability from rare variants.
Yeah.
By filtering it, does it mean that the estimate of additive heritability that we get from GREML
Mhm.
is an overestimate?
It depends on the distribution of the causal variants. If the causal variants are more common, right, than the actual SNPs that we use, then that will be the case. But that's typically probably not the case.
But according to this graph, would you suggest that the markers are more likely to tag common causal variants from this particular?
That's right. Yeah. I mean, in general, common causal variants are going to be better tagged
Right.
than rare ones. Even if you include rare variants, you've got to include a lot of rare variants to tag about as well the rare ones as you do the common ones. So the reason is actually implicit in this plot. To be able to tag something with a really low allele frequency of like 0.005 or 0.0001 or something, the difference in the frequency has to be minuscule. So you're only going to be able to tag something with an allele frequency of 0.005 with something else that has about that same allele frequency, right? Anything that has an allele frequency, even of 0.01, it's just not going to be able to tag it very well. So rare variants are only well tagged by other very rare variants, whereas common variants, right, you see over here, can be tagged by things with a lot of differences in their allele frequencies. So here, if we're using something like 0.4, we could have a variant that's, 0.17 different in its allele frequency and still be able to tag it at a R squared of 0.5.
Right. I'm just wondering, does this methodological issue also extend to LDSC? Because in LDSC, you are proving SNPs by their minor allele frequency, and you're including SNPs only with minor allele frequency greater than 0.05.
Mm-hmm.
And perhaps in GREML, that might not really be an issue. I'm not really sure.
Yeah. So LD score regression turns out it's a great method, but it doesn't work well for rare variants. For basically this reason. It relies on it relies on the fact that things that are tagging a lot of other things should explain more of the variance. And that doesn't work well for rare variants because rare variants really just aren't tagged by anything else other than itself for the most part, right? So they just don't have many LD friends, so to speak. I heard that Ben Neal really wanted to call LD score regression originally. He wanted to call it the LD friends regression, and people thought that was just a terrible idea. So I think we can thank Mark Daly for the fact that we're not saying LD friends regression rather than LD score regression. Okay, so let's think a little bit more about this, and I've only got a few minutes left. So this is probably I won't probably get into the effects of stratification and assortative mating on these estimates. I might just kind of flip through those slides just to tell you what they are. So LD, okay, so effects of SNP and SNP-CV LD on. So LD among markers and between markers and CV. This is stuff that was written in the appendices of the Yang et al. 2015 Ancient Genetics paper, and this derivation was derived by Mike Goddard, who actually has done a lot of the derivations for the GREML method. So I'm not going to say that Mike Goddard is the brains behind the outfit. That's certainly not the case because Jan is brilliant and Peter is brilliant. But Mike has been around and thinking about this for a very long time, and a lot of kind of what's going on behind the scenes mathematically in these methods was thanks to Mike Goddard. So you might, if you want to really get into these methods, read some of his papers. He's a really talented scientist. So what Mike derived is that the heritability of the SNP heritability is equal to the total heritability of the trait multiplied by this ratio. Okay? And this ratio is R squared, the average R squared between the causal variance and the markers. And Q here stands for QTL, which is what a lot of people used to call causal variance, but we've kind of switched over to calling them CVs, but QTL used to be the nomenclature. So this is the average R squared across all the causal variance with all the markers, okay? Divided by the average R squared between the markers among all the markers themselves, okay? So R squared QM, that's what just said here, R squared MM average LD between all the markers. And so here's the same plot that I just showed you a second ago. And you might imagine this R squared QM, if the causal variants are rare, right, they're not going to be very well tagged by common markers. And therefore R squared average R squared QM is going to be lower than the average R squared MM between the common markers themselves, right? So if the causal variants are rarer than the markers, R squared QM will be lower than R squared MM, and therefore that ratio will be less than 1. Therefore, we'll be getting an underestimate of the heritability. If, on the other hand, it's the reverse, and the causal variants are more common than the markers, then the causal variants are actually being tagged better on average than the markers are among themselves. And so R squared QM over R squared MM will be greater than 1, and we'll get an overestimate. And this is exactly what we saw when we looked at these statistics in our data. So here, where we use just common array markers and common causal variants, we get an unbiased estimate because the estimate of R squared QM was roughly equal to R squared of MM. When we looked at this overestimate due to very common causal variants, we observed that the R squared QM was greater than the R squared MM. And this, by the same token, same thing with the more normal case where the causal variants were rarer than the SNPs that built the GRM. We saw an underestimate because the R squared of QM, the average R squared between causal variants and markers, was lower than the average R squared among the markers themselves. It turns out that this formula also explains the biases due to stratification that occur, independent of the effect that the bias that stratification might have if it's confounded with environmental sharing. All right, we'll get to that in just this. If I have time, I'll talk about that very briefly. Yep, Jonathan.
So maybe you'll get to this, but if not, what architecture is more representative of height, resolution, and angle? For instance, I guess if you do Rimmel by different MAF bins, I guess then you get this unbiased estimate, and which one would it correspond to?
We will get to that. I mean, I think the issue, this is kind of where I'm going next. I think the issue is that we really don't want to be using a single GRM to estimate these because it depends so much on getting this correct. It depends so much on whether the markers we happen to use, how they conform to the distribution of the causal variance. And so what we want to do is actually bin those GRMs by their MAF and therefore get a much better estimate of heritability that's not going to be so dependent on the allelic architecture of the trait. So for height, I guess height is going to be, almost everything is going to be more similar to this, okay? But it's just a matter of how underestimated it is. For height, you know, if it might be something like right here, and for IQ, it might be something a little bit lower down here. We did look at this in the UKB, and so that's where I'm getting those numbers from. So the way to correct for this is to bin the GRMs according to MAF. All right, so we can correct for this by binning the SNPs, our markers. We bin those into MAF categories. We can also do the same thing by LD categories, and this is just by regional LD and 200 KB blocks. We're looking into this now about SNP by SNP LD. If you bin these, then within each of those bins, right, the R squared QM is going to be much more similar to the R squared MM. Okay? And because of that, we can get basically unbiased estimates for each bin about how much variance is being accounted for by each of those bins, and we sum across those bins, we'll get a much closer estimate of the total heritability.
Can you just sum them, or isn't there an issue with like double counting? Like if the SNP is in one bin, it's also going to pick up some of the variance explained.
It's kind of like multiple regression, where that's going to be
so that's how
accounted
you handle
for.
it.
Yeah.
Okay, so
Yeah.
the summing thing is just for intuition.
Yeah.
Okay.
Yeah. So GCTA will partition the phenotypic variance among all the GRMs plus some error, and the sum of those is going to be equal to the total heritability. And the partition estimates, by partitioning these, we're also going to be able to explore the allelic architecture, or the kind of the distribution of the causal variance underlying this, which is exciting, I think. So this next slide is messed up because I'd done it in PowerPoint, and it was supposed to be one of these multiple. I should have broken it up. But anyway, this just shows, in essence, what our 3 bins were for this simulation. We binned very rare stuff, low frequency, and common variance into 3 different bins. I don't think we did LD stratified for these results. Within an MAF stratified GRM, the allelic spectra of CVs is necessarily going to be similar to the MAF of the SNPs, and therefore the average R squared MQ is going to be similar to the average R squared MM within each bin. So we should not be having this problem of this discrepancy between those two if we're binning by MAF. That doesn't mean we won't get discrepancies for other reasons. So it could be the case that causal variants are typically lower LD, have lower LD than the markers do themselves, in which case we're right back to this. But by binning by LD, we hopefully will get around that issue too. And so this next slide just shows in black our original, our original estimates, and the triangles are the estimates that we get by doing the multiple GRM and looking at the total heritability across those. And these are pretty much spot on. So not being biased by the discrepancy of MAF and causal variance. We can also try to partition the variance into the different bins. And so this is just a very simple example of doing this. But when we look at just the common causal variance, all the bins, all those other bins basically get explain 0 of the additive genetic variance, and only the common bin explains it all. And the same thing when we do it for very rare. So for very rare, that bin is explaining most of it. You get some due to LD, which is why this is a little bit lower than exactly 0.5. But for the most part, we're able to understand that, okay, well, indeed, this phenotype is actually being caused by rare causal variance. And so this is an extreme example, but if you do this in real data, you'll be able to get some sense. And we've done this for like IQ and for height, and you get a sense of where the causal variants are lying. So for height, most of the causal variants are pretty common. For IQ, it's still the case that most of them are common, but you get a much higher proportion of those that are rare than you do for a trait like height. Yeah.
So are you going to run into these kinds of problems anytime a certain class of SNP is overrepresented in the causal variance? So like for example, if we think that causal variants are overrepresented in coding regions versus non-coding regions, is that going to mess things up as well in the same way?
It shouldn't. I mean, so long as the LD between the markers and causal variants is no different than those between the markers themselves. If there's some reason that being in genes, for example, biases that ratio, then that would bias things. And that is a concern because there's thoughts that things that are important might be more likely in DHS sites, and DHS sites have typically lower LD.
But it'll be captured if you partition.
If you partition it by a LD, then you should be okay. But there's, this is...
Would you ever need to partition by MAF then? Because if the only thing is about LD, then couldn't you just partition by LD and that's all you need?
I guess you could, but I think it's just going to be a lot tougher because you're going to have a lot of LD partitions. So I think you're probably better off doing it by both MAF and LD. I don't know. That's interesting thought.
Actually, there's an interesting history of this. So I would say the first to realize that GCTA is biased by this LD thing was a guy named Doug Speed.
Yep.
Although he didn't fully understand it, but he sort of understood.
Mm-hmm.
And so then Peter's group fired off a letter to the journal saying, no, you're wrong. You can partition by MAF and our estimates become unbiased.
Mm-hmm.
And then basically in the same issues, Speed and Doug Balding responded by saying, well, bin by MAF, but then choose the causal SNPs within each MAF bin to be the ones that are in the
Yes.
LD with their neighbors,
Yep.
then we can still mess things up.
Yep. That's right. Yeah.
Then I think that pretty much convinced everyone that okay, LD is the problem. But then it's exactly like Matt said. How do you bin by LD? I mean, so various approaches have been tried. Speed has his method. The Nature Genetics paper that Matt was referring to, they have this thing where they average LD across big blocks and then create bins that way. So all of these methods seem to me kind of ad hoc. None is guaranteed to work perfectly in every situation.
Yeah.
You can see what it seems to me.
Yeah. Well, this is the argument that Speed and Balding are making in their most recent Nature Genetics paper, which I found very unsatisfactory. Which is that, well, the estimates that you get from these methods depend crucially on the assumptions that you make, and we just happen to we think that the assumptions we're making are better than the assumptions that GCTA is making. That's really where they ended up in this last paper. We submitted our paper not knowing that that paper was in the pipeline at Nature Genetics, and they got accepted, and we knew, oh crap, we're going to have to address these issues. And so when we got the reviews back, they said, well, you've got to, of course, address this issue. So this paper has gotten drawn into this whole debate. We didn't mean for it to be, but now it's kind of, and so we're in the middle of doing all these various types of simulations. It turns out that so this is maybe this is a whole other thing we can get into. There's kind of two different sources of bias that Speed and Balding are talking about. One is, what is the relationship between MAF and effect size? That turns out not to be very important.
Yeah, I agree.
The other one is, what is the relationship between effect size and LD? That one is the one that really becomes crucial. And Speed and Balding are really trying to, wow, I've got to think about this camera being on. I have no problem with Speed and Balding, by the way. I think they're fantastic. This is how science works, right? But I disagree with the way that they're going about this, because they're trying to use a single GRM, and they're really kind of hoping that nature works the way that the way that they're weighting the GRM, that nature works that way. And if that isn't the case, they're going to get biases, and we've demonstrated the biases can be pretty big. I think a better approach is to kind of partition by GRMs. Now there's a downside to that, which is that standard errors become large and you need big sample sizes, and can be fitting problems. But partition by different annotations that make sense, MAF or LD, and hopefully SNP by SNP LD will be even better than the way that Yang et al. Did in 2015, and then kind of let the variant play out wherever it should come out, without having to kind of force these strong assumptions on the data that if they're not met, you're going to get a bias. And we've demonstrated in our paper that that method of LDMS, right, partitioning by MAF and LD, tends to be robust across a lot more violations of assumption than the LDAC method does. But there's always caveats, and so we're kind of in the middle of doing this right now. But we'll see how this whole thing plays out. Okay, so I'm nearly out of time. Let me just race through a few real quick kind of conclusions, and then we'll cut this off. So just real quickly, I'll talk about this issue about that stratification leads to LD. I'm not going to have time to explain exactly why that happens, but if you have allele frequency differences between populations, that will in itself induce long-range linkage disequilibrium between markers. And that is something that's can be a real problem, but if you partition by MAF, because this is being driven by MAF differences, if you partition by MAF, it turns out that doesn't create biases anymore. So if, let me just real quickly, this is kind of weird. So this is what we'd seen before, right, with the unstructured samples, the samples without stratification. We get the opposite biases in a stratified sample. You actually get overestimates for very rare common causal variants, and that's because those very rare causal variants tend to be basically ancestrally private, and they're being tagged by other common causal variants that differ a little bit in their allele frequencies. So you get the opposite set of biases in a stratified sample than you get in an unstratified sample, which at first this was really perplexing, but when you looked into that R squared QM over R squared MM, everything made sense. we stratify by MAF, and that effect goes away. So once again, another example where LDMS performs well, another motivation for using LDMS over something like LDAC that uses a single GRM. And finally, I'll just talk really briefly about this. I mean, I knew I wouldn't have time to get into this, but we've been doing a, oh, I see, this is going to be a problem because it's going so much slower. We've been doing a project about how assortative mating affects these estimates of heritability. This is the ratio of the number of samples to the number of markers. And you can see that the G-Rimmel estimates, these are the G-Rimmel estimates. This is the true equilibrium heritability under assortative mating. These are the Haseman Elston regression estimates. That's our predicted, and this, where we're getting it wrong down here, is no longer a problem. That was due to some problem with our simulation. So we're actually getting it spot on with our algebraic prediction of the Haseman Elston regressions. We haven't been able to closed form predict this, but it obviously is following a very kind of systematic bias. It's being affected by the ratio of the sample size to the number of markers. And there's a reason that happens that I'm not going to have time to discuss. But the long and short of this, I'll just get to the end, is that assortative mating will create biases in these estimates. And these, how big these biases is not necessarily trivial. For IQ, we expect that those to be overestimated by about 25%. This does not account for the effects of natural selection, which would work in the opposite way. And the real problem with this, and this gets back to the question, the answer I had yesterday, where people said, "What do you worry about?" I worry about this kind of thing, where we're just never going to actually be able to get at some kind of true heritability estimate, because there's these biases due to assortment or due to natural selection, and we really don't know exactly how those are working. And therefore, the estimate of SNP heritability is never going to, even with sequence data, is not going to be the true estimate of the true heritability in the population, because you've got to meet these various assumptions. So anyway, let me just, and we've, by the way, this assortative mating bias predicts particular pattern of results, that the G-Rimmel results become increasingly different than the Haseman Elston estimates as the sample size gets bigger. It's exactly what we see in the UK Biobank. So we think this is actually going on for height. When we looked at the same thing for IQ, we did not see this, which could mean that the effects of natural selection are counteracting almost exactly the effects of assortative mating on LD. I don't know. So this is where things get complicated. So that's the IQ results. So in summary, that's the summary, AM bias summary. I'm not going to go over that. So in summary, there's been a lot of excitement about using SNPs to estimate heritability. Large sequence reference panels allow SNPs to be imputed down to very low, minor low frequencies. And in principle, that estimate of H-squared SNP we get is going to approach the true heritability. And that also, by the way, will allow investigators to understand the allelic spectra underlying traits, of the causal variants underlying traits. But it's crucial to understand the factors that can bias those estimates. We've shown that LDMS tends to alleviate those biases due to MAF and due to LD, but we can't figure out how to get rid of those biases that are being caused by things that aren't intrinsically related to MAF, like stratification. Like assortative mating. And I think it's going to be the same kind of issue with natural selection. So I'm sure that there's people who are thinking about along these lines. Maybe James is as well. So I had this thing about best practices, but we're over time, so I think I'm just going to end it there. So thanks.